So now that we're done with the nitrogen and oxygen relationship, or the little dip there, there's also another one right here between beryllium and the element boron. So it also dips just a little bit, but the logic also applies here. If you look at lithium, I'm sorry, beryllium. Beryllium actually has, again, a full 2s2 orbital. And that's where the ionization would be pulling from if it was to take an electron. Right here, though, with boron, right, boron is not only what I'm doing, but is actually going to have one electron in the 2p orbitals. So if it's going to remove an electron, it requires a lot less energy for the 2p1 to be removed. Because if you remember from, again, from the previous little section here, if you have a full set of orbitals, this is going to be fairly stable and therefore is going to require more energy to remove it. Because if you remove it, it becomes less stable. Granted, it does become half full, but being completely full is way more favorable than being half full. So that's why this one right here ends up having a lower ionization energy. And this applies for every other situation where you see that little dip right here. So this to here, and even from here all the way down to this one, these two you can also see a noticeable dip, and then this one as well. Right? So therefore, again, applying the orbital concepts of knowing what's full and half full, you can tell which one's going to have a higher or lower ionization energy. Moving on, successive ionization energies. So hopefully most of you know what successive means, meaning one right after the other. Typically speaking, with the first ionization energy, this removes the first valence electron. And the second ionization typically also removes a second valence electron after the first one has been removed. And this can go on for the third, fourth, etc. until you eventually want to stop. But kind of the idea here is that you need to understand what's going to happen to the ionization energy. So what is the actual value as you continue to ionize one electron after the other? So of course, as we're talking about ZF, you need to include this. ZF, as you remove more and more electrons, should basically, for the most part, remain the same. This, of course, depends on the number of electrons. But for the most part, the ZF should remain the same. So with each successive ionization, you shouldn't expect this to all of a sudden become bigger or smaller. But what does happen, though, is that you can actually use electric configurations to help you really figure out and know what the ionization energies are. So let's go and take a look at a couple of examples here. Let me start off by using the arbitrary element, aluminum, again. So aluminum right here has the electric configuration of 1s2, 2s2, 2p6, 3s2, and then 3p1. So after it ionizes this first one, this 3p1 goes away, right? So what you're left with then is all this, and then 3s2. One is aluminum plus 1. When you take your second ionization energy off, or use your second ionization energy, you remove this 3s or electron, but you're left now with 3s1 after the second ionization has been completed. And then your third ionization will remove that one from it. So this should kind of make sense. If I take a look at the actual values, you'll notice that the aluminum, as you continue to remove more and more, the aluminum ionization energy will increase with each successive ionization. Why is that? Well, again, remember that whenever we ionize something, or especially when we remove an electron, you have the same number of protons, so your ZF remains constant, but the number of electrons continues to decrease. So as these go down, the effective nuclear charge is distributed amongst fewer electrons, therefore it holds on to them tighter, and therefore requires more energy to remove them. And of course, the more electrons you remove, the tighter the remaining ones are being held by your effective nuclear charge. Therefore, the more electrons that continue to, the more ionization energy that's needed to remove them. So overall, your ionization energy will increase with every successive ionization. Now, this one you notice also there's a kind of a pattern here. I'm just going to pick, again, aluminum, as you saw from earlier. So aluminum, my first ionization is 578 kilojoules of energy. Again, I have to put in 578. My second ionization is 1817, and then my third one is 2745. Right, so again, you notice that it's increased with each increasing ionization. Now, you also notice that right here, actually, this is a huge jump, right? So going from this to this is probably increasing by a factor of about 3, right? Multiplied by 3. And then the next ionization is actually a little bit less, quite a bit less than half, but you still increase by quite a bit from here to here. However, the jump from this ionization to this ionization is quite significant. I mean, you're increasing it by a factor of 5. And this is fairly small. Some of the other ones increased by a factor of 10. I mean, this one's almost a factor of 10. This one's a factor of about 7-ish, probably more like 6. But you kind of get the pattern here, you get the idea. These, again, you notice it kind of jumps by a little bit, but then from this one specific one, it also increases by a lot. And notice that it kind of makes this little pattern here, and that should be obvious in just a moment. Anyway, so this right here, again, how can electron configurations help us visualize ionization energies? We've covered this, the 3s1, the 3s2, 3p5, so on and so forth. This one, again, we have to remove a lot of them. I know tempting for us to think that chlorine is just going to add an electron here for its ionizations, but remember the definition is that we're removing them. So it becomes 3p4, 3p3, 3p2, so on and so forth. And each one, of course, has an increasing value. One thing I kind of forgot to mention here, and I think actually, let me slide back a little bit here. One thing I forgot to mention, though, is why exactly it goes up this way. So as a reminder from the previous slide, you at this point when you've got the third ionization complete, your electron configuration is 1s2, 2s2, 2p6, because you've already removed the 3s1, the 3s2 electron, and the 3p1 electron. So all those are removed, and you're left with this. So why is it that when you try to remove the next electron, it jumps up so high? Well, that's because it requires an immense amount of energy to remove an electron from a noble gas configuration. So this looks just like a noble gas, right? Without any context, you would think it would be, but it's actually aluminum with a +3 charge. And that's why it requires so much more energy, because you try to remove an electron from an inner shell in a complete electron energy level. So that's why it requires that much more energy. Because if you were to remove it, it makes it that much more unstable, and that's why you have to require a lot of energy. Again, here's a quick review. Enthalpy change of any ionization is always positive, so your delta H is always greater than 1, or greater than 0, excuse me. Atom versus large atom, which one have a greater ionization energy? It should be your small atom, because it requires more energy to overcome the effective nuclear charge pulling on those electrons tightly. Two ways in which ionization energies can be compared. You can look at it either from element to element, so essentially first ionization energy of one element versus the first ionization energy of another one, or you can look at it as successive ionizations. And then which successive ionization would you expect to see a very large increase? And coincidentally, it would be the fourth ionization energy, which would be a very, very large increase. So going after the third ionization has completed, moving on to the fourth one, this one you would see a very large increase. This can apply to any element. So for example, if you want to use, say, beryllium again, beryllium has 2 valence electrons. The second ionization energy isn't too bad, but that third one, trying to remove the third electron from beryllium, would be a very, very large value. This one right here is called the photoemission spectroscopy. This is very new to the curriculum, but this is essentially an application of the photoelectric effect. And what this does is it allows you to ionize samples and then figure out something called the binding energy. The binding energy essentially is another term for how strongly the protons hold on to its electrons, which is then another term for effective nuclear charge. Essentially, you treat elements with light, and then you analyze the electrons as they're emitted away from it. So this right here is your sample down here on the ground, or on the base. You shoot some sort of light on it, and then that light is supposed to eject these electrons, which sent through this analyzer essentially uses magnets to guide the particles and see what it is you get out of it. Now, the graph that you get out of this, though, is actually a spectrum, right? So it's a photoemission spectroscopy. So you should be producing a spectrum, and it produces this graph or spectrum that corresponds to specific electrons and where they are. So are they electrons in the 5s orbitals? Are the electrons in the 3d orbitals? Electrons in the 1s orbitals? This will tell you. So the photoemission spectroscopy is actually a pretty useful tool. Let's go and give you a couple of examples. This one right here is neon. So neon, notice, is fairly simple. Right now, take a looking at the graph. The binding energy, so essentially the effective nuclear charge, the binding energy is actually done kind of an opposite in this example, because meaning that the largest value is over here on the left and the smallest over here, 0, is at the right. Normally, again, you would think a little small on the left, large to the right. It kind of depends on your situation. And this tells you the relative number of electrons. So all the way through here, they don't really have a whole lot. This is kind of just like little wavy lines represent noise. It's kind of just background noise. And here's the part that actually matters. So this is the peak that appears here. This is the peak that appears here. And there's another peak here that appears here. And then again, each of these are independent of each other. Now, we can actually identify all the parts of this atom based on our individual peaks. One thing you should know is that all the electrons in the same subshell, so basically all the same in the degenerate orbitals, have the same binding energy. So all these right here are part of the same set of orbitals. There's one peak for every type of electron, meaning in each type of orbital. And the peak height or area corresponds to the relative number of electrons in each subshell. And there's mathematical programs that you can do this with, but if you integrated this area, then you get the area underneath the curve, the peak anyway, that would tell you a certain number of electrons. But in this case, it's easy just to do it by height. So this height right here and this height right here are about the same. So these two have the same number of electrons. And this right here is much taller, so this one also has a certain number of electrons as well. One thing you should also probably put together here, as effective nuclear charge increases, the binding energy also increases, and I think that's something we mentioned before. Now, how should we interpret this? Well, notice that again, your spectrum of neon, this neon, should have a configuration of 1s2, 2s2, 2p6. So you really have three different types of orbitals that are filled here. So your electrons, again, are assigned to these three different places. You should be able to identify which peak goes with which one. Now, the lowest energy ones, right, so looking at the binding energy, the lowest energy ones are typically the ones that are furthest away. And it makes sense because your 2p6, because it's in the highest energy level here, again, 2 is greater than 1, it's in the highest energy level here and also has 6 electrons, therefore having the highest peak. This you can probably go ahead and attribute to being the 2p6 electrons. Again, not only does it take the least amount of energy to remove, showing you the lowest binding energy, but also it has the highest peak, which suggests it has the most number of electrons. B and A. Well, both these, again, have the same number of electrons. You can expect that because you have the 2s2 and a 1s2. But which one is which? Well, same logic as before, since B has typically the lowest, or B has a lower binding energy. That means that the protons are holding onto the electrons much less tightly than these right here, because this has a much higher binding energy. So between these two sets of electrons, which one's probably B? It's probably this one right here. So this one you would expect to be your 2s2 electrons. And that leaves this one right here to be your 1s2. And this makes sense to be the highest energy ones and binding energy because it is the closest to the nucleus. So that would have the most amount of attraction towards the nucleus. All right, let's try another one. This one right here, I'm not going to identify what it is just yet, but you can kind of take a look. Here's another example. This one, again, the graph and way it's represented, notice it goes from 0 to 10 on the bottom one, but then goes from 10 to 100. So this is kind of like a broken up, or at least a spectrum that's been broken up a little bit. And you'll see this from time to time. Let's go and take a look at the energies. You have a set of 2 right here, you have a set of 4 right here, and you have a set of 2 right here. Now again, the reason why this can be confusing sometimes is because you also have this inverted from what we had before. It goes from small to big, whereas before it was going from big to small on the previous slide. Now let's go and break this down. So this right here, you have a set of 4 of them, this one you have a set of 2 of them, and this one you have a set of 2 of them as well. So you have a total of, again, 8 electrons. Most of you can probably figure that out. Well, that's probably associated with oxygen. Well, let's make sure we know what specific parts are here. Well, this right here, if you have 4 of them, and they're the lowest in energy, meaning they require the least amount of energy to remove, that's probably in your 2p4 orbitals, or at least your 2p orbitals, and there's 4 of them. This right here is the next highest, meaning it's going to require a little bit more energy to remove. That's because it belongs to your 2s2 electrons, and these right here are representing your 1s2 electrons. Let's go and take a look at this one right here. I'll actually give you a moment, so you're just going to pause here for just a second. Try and figure this one out yourself. Obviously, this one's a little more complicated, but I think you'll be able to do this one. Okay, all right, so let's go and try this out. Now, this one right here, because it is the highest in energy, again, going from 100 to 500 on the scale, this is highest in energy, so this is actually probably going to be your 1s2 electrons. Moving on, going from 0 to 100, you have these two right here. Judging by the scale and also the distance, this one requires less and this one requires more energy. Judging by those energies, you should also be able to predict that this is going to be a 2s2, and then this will be a 2p6 electron. Right, now the bottom one, again, you see this right here. You have, again, 2 more that you have off to the side. This one requires very little, so that means this is not held on very tightly, whereas these two are a little bit more tightly, so these are probably not the same energy level. Let's find out. This might be a 3s2, and this would be your 3p6. Again, further away, requiring less energy to remove. And also meaning that there's less binding energy. This one's also a little bit closer, that's why it's a higher in binding energy, therefore it's held a little bit tighter by your protons. And that makes this right here then probably your 4s2 electrons. And it more or less matches the pattern in which you fill electrons. So if you go through the periodic table, you can probably see that this has 20 electrons, and therefore is the element calcium. And one more example, you can try your own, and you can figure out what this is in just a moment. Okay, and by counting this out, or figuring out this is going to be your 1s2, is your 2s2, your 2p6, 3s2, and then 3p3. So that is phosphorus.